Okay, sorry about that. Stream got disconnected. So we were discussing that an infinite sheet and which having a charge density of sigma, then its electric field is standard formula, that is our 2 epsilon naught and our z unit vector. Okay. And this is the point which is above the sheet, and for below the sheet the direction will be reversed. Okay. And we can also write for our part 2. So you can say that our field on the axis of a uniformly charged disk at height z, okay, and we can write that formula as our electric field due to disk, and this will be in z direction both, will be equal to sigma upon 2 epsilon naught, and this comes as 1 minus z upon z square plus r square and z unit vector. Okay. And so net electric field will be nothing but the subtraction of both. Therefore we can say that electric field of a sheet with a hole. Okay, that was our question. So we can say that electric field will be equal to electric field because of the sheet minus electric field because of the disk. And we can just substitute because we found out both. This is sigma upon 2 epsilon naught minus sigma upon 2 epsilon naught and 1 minus z, and this comes as z square plus r square and its square root. And if we simplify it, we are going to get this as electric field in z direction will be equal to sigma upon 2 epsilon naught, and this will be our z upon, because we can take this as common, so this will be 1 minus 1, and that will be cancelled out. So this comes as z square plus r square and square root. So this is the electric field at a point z on the line L. Okay. So this was the first part, and in part B we have to find out the oscillatory motion of the charge near the center. Okay. And it is given that charge minus q mass m is released near the very close to center, that is very close to z is equal to 0. So we can use the approximation, and we can say that our z is very much smaller than our r, therefore we can say z square plus r square and square root can be approximately equal to our r. Therefore, so this is our equation number 1. So we can say from equation 1, we can write that our electric field will be equal to approximately sigma upon 2 epsilon naught, and this comes z upon r. And because this charge is opposite and our sheet is oppositely charged to this one, therefore we can say that the force on the charge, let us call that F, and F will be equal to minus Q and the electric field E. So we can write that force in Z will be equal to minus electric field we just calculated is our, this will be Q times sigma, and we have this as 2 epsilon naught r and times Z, and this is nothing but minus k times Z. Okay. So we can say this is nothing but our restoring force. Now we can write the equation of the motion. So f of z will be nothing but our, you can say, equation of our motion. This force is going to produce acceleration. So in terms of z, we can write this as m double derivative of z is equal to minus q sigma upon 2 epsilon naught r times z. And this is a standard form of SHM, acceleration plus the omega square times z is equal to 0. Therefore, we get that our omega square will be equal to our q sigma upon 2 epsilon naught times r. Or we can say our omega is equal to square root of q sigma upon 2 epsilon naught r. And we are also given the values. So we are given that mass is given, everything is given to us, so we can easily find out all these things. So let us substitute it. And here I missed one thing, that is mass. Okay. And so we get our omega will be equal to, charge is given at 10 to the power minus 8 and density is our 10 to the power minus 6. This is 2 epsilon is our 8.85 into 10 to the power minus 12. Radius is given to us as 0.1 and mass is given as 1 gram, so we can say that is 10 to the power minus 3 kg and its square root. So this approximately will be equal to 2.4 radian per second. And now we come to part C, and part C states that we have to find out the speed at the center of the hole. Speed at the center of hole. Okay, and this is our part C. For that, we are going to use energy conservation. So for this, we are going to use our energy conservation. Okay. And we already know that our electric potential on the axis will be the potential difference between the position Z as well as the center. Okay. So we can say that the potential difference between position Z and the center, and we can write that as our potential at Z minus potential at center, means Z is equal to 0. And this formula we already know, that our Vz minus V0 will be equal to minus, and this will be integral of our E z prime, and this comes as a dz prime, and integration is going to vary from 0 to z, because center is at 0 and our this, okay, and this z prime is nothing but different variable, so that we do not confuse it by the z. That's only signaling, otherwise it doesn't matter. And so we substitute this electric field, so we get this as minus sigma upon 2 epsilon naught 0 to z, and this comes as z prime divided by z prime square plus r square and square root, and this is our dz prime. Okay. And this integration is quite easy to solve. We are going to put simple our u is equal to our z prime square plus r square. So du will be giving us 2 z prime and dz prime. Okay. Or we can say duu by 2 will be equal to a z prime divided by dz prime. Okay. So we can just write that our Vz minus V naught will be our sigma upon 2 epsilon naught, and we get from here as our z square plus r square minus r. Okay. And now we can use our energy conservation. Initially it was said that it is being released, so it means initial velocity is equal to 0, so therefore initial kinetic energy is equal to 0. Now we are using the energy conservation, and our initial kinetic energy will be 0 because it is released from a height h, z. Okay, and final at the center is suppose v, so therefore we can say that our final kinetic energy will be equal to our half m v square. Therefore the difference between the two, we can say this is our half m v square will be equal to q times the potential difference, that is our point z minus the center. So we already found it, so this comes as our q sigma upon 2 epsilon naught, and this comes as our z square plus r square minus r, and velocity is equal to, here this 2 cancel out with 2, and we get this as our q epsilon q sigma, and we have m epsilon, and this is our z square plus r square square root minus r. So this is the velocity at the center of that disk. And it is also given asked that what happens to the velocity whenever z is very much larger than r. So under this condition we can assume that our z square plus r square is square root is approximately equal to z. So therefore our velocity equation will epsilon, and this will be equal to our, one second, yeah, I forgot to add square root here. and this comes as our sigma times z, and its whole square. So this will be our velocity under the condition that z is very much larger than r. Okay. And this was our second question. Now we come to our third question, and in the third question it states that a point charge q is located at the origin. Consider the electric flux through a circle at a distance, this distance should be L, from Q, subtended at angle 2 theta as in the figure. Since there are no charges except at the origin, any surface that is bounded by the circle and the space to the right of the origin must contain the same flux. Calculate this flux by taking the surface to be, so we have two types of surfaces that is given: a flat disk bounded by the circle, part B, a spherical cap with a sphere centered at the origin bounded by a circle. So here the hint is itself given in the question. It says that there is no charge except at the origin, and any surface bounded by the circle to the right of the origin must have the same flux. Okay. So it means in part A as well as part B, the surface which we are is asked to for the discussion or in the question is lying toward the right of the charge. Okay. So this is a charge, so both the surfaces are lying to the right of it. So in both the cases the value of the flux will be same. Okay. And we can solve this same question by using our solid angle as well as the more traditional way. Okay. So let us start with our more traditional way, then we can come to back to the solid angle. And so we can just point it out here that any surface bounded by same circle and not enclosing any charge has same flux, So it means both our option A and not option A but part A as well as part B, they are going to have same answer. Okay, because the charge is not enclosed by any of the surface. So the flux passing through both will be same. And so let us start with our solid angle, then we come more to a traditional way. So we can say the flux and the solid angle, or we can say for a point charge, for a point charge, we can write our flux phi will be equal to Q upon epsilon naught divided by our solid angle, and this is our 4 pi. Okay. And this solid angle omega is defined as a solid angle subtended by the surface on the charge, Okay. And in this case we are given that our half angle for our cone is given to us as our theta. Therefore, we can write that solid angle of the circle or we can say that circle subtends a cone of half angle theta at the charge. Therefore, this formula is also standard. We already know because of this conical shape of the, because here we can clearly see the shape of the surface at this charge is a cone, conical one. Therefore, we can say that solid angle of the cone, that is our omega, is equal to 2 pi 1 minus cos of theta, and we can just substitute it. So we get our flux phi is equal to q upon epsilon naught, and this comes as our 2 pi 1 minus cos of theta and 4 pi, which gives us q upon this pi, and 4 goes by 2, q upon 2 epsilon naught 1 minus cos of theta. So this was our part 1, and we come to part B. And part B states that the spherical cap is bounded by the same circle. We have a spherical cap bounded by same circle. Or we can say that the cap lies on the sphere centered at the charge. So from here we can say that the cap lies on the sphere centered at the charge. The sphere is centered at the charge. Therefore, we can say that the electric field, or we can say the field, is radial and perpendicular everywhere. It means we are going to have the same solid angle, or we can say we are going to have same flux. Therefore, our flux in case of part B, that is for cap, will be also equal to q upon 2 epsilon naught, and this is 1 minus cos of theta. So in part A as well as part B, we are having the same value of our flux. Now let us use more traditional method. Okay, so without using a solid angle, we can also solve it. Okay, so let us try that. So we know that for a point charge at the origin, for point charge Q at the origin, the electric field at a distance r, the origin, the field at distance r, So we can write this as electric field is equal to 1 upon 4 pi epsilon naught q upon r square, and this is a r unit vector. Okay. And let us draw a circle, and this is the axis of the circle, and it is having a charge q, and the distance is our L, and the radius is our A, and this angle is our theta. So we can say the circle subtends a half angle theta at the charge. You can say that our circle subtends half angle theta at the charge. So it means that we can find out the radius of the disk. You can say the radius, which is A, radius of the disk, which is A, will be equal to L tangent of theta. Okay. And let us consider, okay, let me draw this disk, but now I'm going to draw this disk in a horizontal way, okay, like this, because it is much more easier to draw. And we are having, suppose this is the axis of it, and we consider a small area dA in the disk. Okay. This is a small area dA, and its radius is, let us suppose, consider as rho, and the charge q is somewhere here. And therefore, and let us assume that this disk is making an angle of alpha with the axis. And we also know that this direction of an electric field will be something like this, and let us draw a normal to the surface also. This is an unit vector, that is a normal vector. So obviously this angle will be also our alpha, and we already know that the original disk is making angle of theta, and this distance is our r, and this is our fixed, that is our L. Okay. So we considered a small element, and let us suppose this small element dA is having a charge dQ. Okay. So you can say small element dA of radius rho from the center of the disk, from the center of the disk. Okay. And the angle between the electric field and the normal is our alpha. You can say the angle between electric field and area normal which is denoted as our n unit vector, is alpha. Therefore, we can write that our cos of alpha will be equal to L upon R, And we can also say that our one second. Sorry, my mistake. This is not R, but this is R. And therefore we can say that our R will be equal to L square plus rho square and its square root. So because of this small area element dA, we can say that the flux, therefore we can say that the flux will be equal to our electric field and our small area dA. And electric field will be our E cos of alpha and our dA. And dA we can find out because our area is nothing but pi rho square. So dA will be equal to 2 pi rho and d of rho. Therefore we can say that our flux will be equal to, we can substitute value of our electric field, and that electric field 1 upon 4 pi epsilon naught q upon r square L upon r, and area we get this as our 2 pi rho and derivative of rho. And here we can cancel out this pi, 2 and 2 goes away, and what else, rest of the things will be same. Therefore we get that our d of phi will be equal to, this comes as 1 upon, let me write this as ql, and we have this as 2r cube, and we say rho d of rho, anything else, okay. This is our q. So this is a small flux due to our this small area dA. Now for our complete disk, so we can say for complete disk, this will be nothing but integration of our d phi, and same we are going to write for our right side also, q upon L, and this is about 2 epsilon naught integration, and one second, yeah, here I missed epsilon naught, and we substitute value of r, so this comes as a rho d rho, and r is our L square plus rho square, and this comes as our 3 by 2. R we have, this is our R. Okay. And obviously the limits will be from the 0 and up till here. Okay. So this will be 0 and L tangent of theta. Okay. Because whole complete angle is our theta, that is a half angle. So it is going to start from 0 and up till our L tangent of theta. So this comes as 0 and L tangent of theta. Okay. And this integration is quite easy. Once again we are going to put that u is equal to L square plus rho square. So du will be giving us 2 rho d rho, 2 we can just divide it here, and we can change the our limits of integration. That is quite simple, and let me sort it out directly. So we can say that our flux phi will be equal to ql, and this is our 2 epsilon naught, and it comes our L square to L square secant square theta, and this comes as a du divided by, this will be our u and 3 by 2. Okay. And if we integrate it, we are obviously going to get the answer. So that our flux phi will be equal to q upon, this is our 2 epsilon naught, and we are going to have 1 minus cos of theta. So in the both cases, we are going to get the same answer. Okay, whether we use our this solid angle or we use the more traditional way, the answer is going to remain same. Okay. And for part B, we can also use the more traditional way. Okay. And part B, we are supposed to find the flux through the spherical cap. Okay. Flux through the spherical cap. And like in initial discussion, we said that our electric field is normal everywhere. So electric field is normal everywhere. Therefore, we can say that E dot dA can be written as EdA. And so we can write our flux will be equal to 1 upon 4 pi epsilon naught, and this comes as Q upon R square and our dA. And our area of the cap is equal to our 2 pi and R square 1 minus cos of theta. Okay. So we simply substitute this our and get the answer. So we get our flux 1 upon 4 pi, and this comes as Q upon R square 2 pi R square 1 minus cos of theta, and here this R square pi 2 goes by 2, so we get flux is equal to Q upon 2 epsilon naught 1 minus cos of theta. So whatever method we use, whether we use the solid angle or we use this more traditional way, the answer will be same. Okay. And in part A, part B, we have to remember that the charge, any surface which is to the right of the charge is going to have the same flux. Okay, for this particular question. Okay, because the enclosed surface is just to the right of the charge. So this is our charge. Whatever surface we draw to the right of this charge, the amount of flux will be same. So in part A as well as part B, the only difference is how the surface is being drawn, but amount of flux associated with each surface will be same. Okay. So this was our today's 3 questions. Okay. And that's all. Thank you.